Professor Robert Malenka. He's here all the way from Stanford, and he will talk about mechanisms of the prosocial actions of MDMA. Thanks, Rob, for coming.
Thank you. Okay, well, of course, thank you, Prateep, for inviting me and organizing this session. And I can't tell you how pleasing it is as a basic neuroscientist to see how packed this this auditorium is, that there are people who actually care about basic mechanisms and what they might tell us about how this class of substances work. So I started my lab in 1990, before some of you were born, and I've always been interested in using drugs as powerful probes of nervous system function. For a while, I was studying drugs of abuse, such as cocaine and methamphetamine, as again, a powerful way of causing an experience in an experimental animal, and then delving into the brain and seeing what changes occur that account for the behavioral effects. But at least in the early 90s, I didn't think it would be prudent for my career to admit that I had an interest in studying both the classic hallucinogens such as psilocybin or LSD, and never mind a drug such as MDMA, which was getting a lot of bad press, especially in the Bay Area for a variety of reasons. But finally, I came out of the closet about 7 or 8 years ago and published a commentary with my then postdoc, Boris Heifetz, who's now an assistant professor at Stanford and a close collaborator. And we pointed out that studying the actions of MDMA is not, really could provide insight, not only to how MDMA works, but because of its very powerful prosocial effects in human beings, might actually tell us something fundamental about, I think, some of the most important and powerful components of human interaction. And towards the end of my talk, if there's time, I'm going to talk about empathy in mice and how MDMA might actually influence that. Of course, as a psychiatrist who once saw patients, I was also very interested in elucidating the actions of MDMA because, as you all know, it's being tested in a variety of clinical trials, most notably the MAPS trials and using MDMA as an adjunct for psychotherapy. Okay, so Boris was a postdoc in my lab. We teamed up, and he started doing mouse behavioral experiments. And the first thing he had to do was develop a simple behavioral assay for what I'm going to call either social preference or sociability. And the assay he chose to do is actually a fairly standard one. Sorry, I'm having trouble with. Oops, sorry. I can do this. Where is the button? Help me out. No, that's the slides. Did you get it? Which one? The left one? This one. Aha, I did it. Whoops, no. Sorry. Which one? Up here. I'm not going to use the goddamn pointer. All right. So he developed a behavioral assay. He didn't develop it. He used one that's standard in the field, shown in the upper left, which is known as the 3-chamber social preference assay, where you put your mouse in an experimental apparatus. It has 3 rooms. In one room, there's a little cup with a juvenile mouse, and in the other room, there's either an empty cup or a cup with a toy mouse. And you basically ask your subject mouse, which room do you want to hang out in? With the assumption that if it hangs out more around the cup with its little buddy, that's showing social preference or an increase in sociability. So in the upper right in B, what Boris did is a dose response of the effects of MDMA. And what you can see in a dose response, dose-dependent way, MDMA enhanced social preference or sociability in this admittedly very primitive and simple behavioral assay. In C and D, what you'll see is just the time course of the effect. And then in panel E on the lower right, one of my favorite experiments. And by the way, those of you who heard this talk yesterday in Charité, I apologize. It's the same talk. I was too lazy to put together a new talk. But maybe you'll learn something the second time around. So if you look at the bottom right, it's again, one of my favorite experiments. If you look below the graph, you'll see in the second bar, if we gave the MDMA to the mouse that was under the cup, there was a trend towards increasing sociability or social preference. If we gave the MDMA to the mouse that was free to explore, which is the standard way we did this assay, we saw a pretty clear increase in sociability or social preference. And then the last experiment I call the rave experiment. If we gave both mice MDMA, we had the biggest effect, which is actually, it's cute, but it actually may be telling us something about how MDMA actually is working. Okay, so one of the goals of this original project that was published now several years ago was to see if we could mechanistically, either at a molecular level or at a circuit level, dissociate what I'm going to call the prosocial effects from MDMA from what I'm going to define operationally as the abuse liability of MDMA. And what do I mean by that? MDMA is a psychostimulant. It's a part of the same family as methamphetamine and cocaine. I don't think it has nearly the abuse or addictive liability of those drugs, but nevertheless, because it's a psychostimulant, I think it has that potential. So, and I think that's a particularly important point, and Rick Doblin doesn't like it when I talk about this, but the way MDMA is being used in the MAPS trials, I think it is very safe. It's used as an adjunct for psychotherapy. It's only given twice. But I also anticipate, should the FDA in the United States approve the use of MDMA, even with the black box warning on it, that there's going to start being a lot of off-label use of it. And that poses the potential for inappropriate use and perhaps some use that will do some damage. So in mouse work, it turns out that every drug really pretty much ever tested, not only the psychostimulants, but the opiates, nicotine, alcohol, all drugs that have some form of abuse liability have two behavioral effects. One is very simple. They just increase the locomotor activity of your subject mouse. So what's shown on the left is in a dose-dependent way, MDMA at 7.5 milligrams per kilogram did not cause an increase in locomotion, but a higher dose did. Perhaps more pertinent to, in quotes, abuse liability is assaying the rewarding property of a drug, in this case, MDMA. And the gold standard for determining the reinforcing or rewarding quality of a drug is doing some form of self-administration under an instrumental conditioning protocol in your mouse. That's kind of a painful thing to do. So a poor man's version of looking at the rewarding quality of any experience, in this case a drug, is what's known as conditioned place preference, where as shown in the diagram, you give MDMA and you limit the mouse to one specific context, in this case, the gray room on the left. On another day, you give it a control substance like saline, and you put the mouse in a different room. And then on the test day, you ask the mouse, where do you want to hang out? And you assume if it wants to hang out in the room where it had a drug experience, that indicates the drug is reinforcing or rewarding. And you can see at the lower dose MDMA was not reinforcing, but at the higher dose it was. Okay, so what are the molecular targets of MDMA? We already heard from Dietmar that it's well established that MDMA, its major molecular targets, and certainly not its only ones, but its highest affinity molecular target is the serotonin transporter, which we call SERT. It also interacts with the dopamine transporter, which I'll call DAT. It has been reported to cause the release of oxytocin via an indirect mechanism. And there's a lot of indirect evidence saying increases in oxytocin levels may contribute to some of the behavioral effects of MDMA. We're going to focus initially on the role of the serotonin transporter and whether that's important for mediating this prosocial effect of MDMA. So the first thing Boris did is a simple behavioral pharmacology experiment. He gave MDMA IP, but before doing that, he gave a drug called citalopram, which is a high affinity binder to the serotonin transporter, which prevents MDMA from binding the serotonin transporter. And you can see that that prevented the prosocial effects of MDMA. He then took a molecular approach using the modern tools of neuroscience, meaning really a genetic approach. We obtained a conditional knockout of the serotonin transporter, which allowed Boris to delete the serotonin transporter only from the dorsal raphe neurons that produce serotonin. And you can see in panel E, that knocking out the serotonin transporter from dorsal raphe serotonin neurons, it's noisy data, but on average blocked the prosocial effects of MDMA, saying its molecular interaction with the serotonin transporter is necessary. Importantly, in those same mice, if we used a higher dose of MDMA and assayed its reinforcing quality in this conditioned place preference assay, that was not affected by knocking out the serotonin transporter. It also wasn't affected by citalopram. So right there, that tells you that the molecular target that is mediating the reinforcing quality of the MDMA experience, it does not require the serotonin transporter. Okay, so where is MDMA acting in the brain? I hope most of you are neuroscientists and know there's something called the classic mesolimbic reward circuitry, which classically consists of dopamine neurons in the ventral tegmental area that send projections to another key component of this reward circuitry called the nucleus accumbens, also known as the ventral striatum. I didn't have time to go through this, but my lab has done a lot of work doing manipulations that suggest that the release of serotonin, specifically in the nucleus accumbens, promotes prosocial behaviors, promotes social reward, promotes sociability. So given that MDMA was interacting with the serotonin transporter, and I'll show you later, causes a massive release of serotonin in the nucleus accumbens, it was an obvious experiment to test whether directly infusing MDMA into the nucleus accumbens, this is old-fashioned behavioral pharmacology, but I still think there is a place for that in modern neuroscience. And what you can see in the purple bar here is that direct infusion of MDMA into the nucleus accumbens had a very robust enhancement of sociability in this three-chamber assay, saying that its action only in the ventral striatum is at least sufficient for this specific behavioral effect of MDMA. Doesn't mean for many of the other effects, nucleus accumbens is the target. He also did the converse experiment where he gave MDMA IP in the belly of the mouse, and he infused the serotonin transporter antagonist, or the inhibitor, citalopram, directly into the nucleus accumbens. So this is just a test of this hypothesis that MDMA is acting on SERT within the nucleus accumbens. And you can see in the right bar that on average, this manipulation blocked the prosocial effects of MDMA. So we have two different behavioral pharmacology experiments suggesting it's MDMA interacting with the serotonin transporter, most likely on the serotonergic inputs in the nucleus accumbens that's required for its prosocial interaction. Importantly, this is another conditioned place preference assay, infusing citalopram into the nucleus accumbens to prevent MDMA from interacting with the serotonin transporter did not block the conditioned place preference caused by MDMA, whereas a non-specific dopamine receptor antagonist infused in the nucleus accumbens did, which is not unexpected. This is just a panel from a paper we published in Neuron recently on a related but different topic, where we used a genetically encoded sensor of serotonin, which we expressed in neurons in the nucleus accumbens, and then we gave the animal MDMA IP into its belly. And all this what this shows you is that, as expected, MDMA does cause a massive release of serotonin in this target structure because it receives a pretty heavy serotonergic innervation. So, of course, we were interested in the potential therapeutic potential of MDMA. I have a specific interest in autism spectrum disorder for a variety of reasons. So we, in subsequent work done by Jessica Walsh, she obtained actually 6 different mouse models of autism spectrum disorder. I'm going to show you data from 3 of them. This is, these first 2 are genetically based models of autism. What's graphed on the upper graphs is a different assay. It's called the juvenile intruder assay. I'm going to go for 25 minutes and leave 5 minutes. I'm just seeing you test it. I know I always go over. I'm well known for going over. But I flew a long way from California. And I am jet lagged. All right, so the top graphs are, it's a very simple assay. It's called the juvenile interaction or intruder assay. You take your subject mouse, you place a little buddy mouse in its cage. You use a juvenile, so you reduce the normal aggression between conspecifics of the same sex. And what you can see, if you look at the blue bars, you can see that both in that assay and then the bottom graphs show the assay we've been doing, the three-chamber social preference assay, that these autism mouse models have a deficit that is largely rescued by giving MDMA. And then this is a third mouse model of autism. This is an environmental model where you give pregnant moms valproic acid, and for reasons I don't understand, the pups show deficits in a variety of behaviors related to autism spectrum disorder. And again, what you can see in the blue lines is these mice show a deficit in these sociability assays that's rescued by MDMA. How is MDMA working? It's going to be complicated, as Dietmar beautifully showed you. Serotonin causes the massive release of serotonin. What did I say? MDMA causes the massive release of serotonin. I think there are, 16 or 17 different serotonin receptors in the brain. So it's really hard to figure out which of those receptors, the released serotonin caused by MDMA, is critical for the behavioral effect you're studying. For a variety of reasons based on previous work, we were specifically interested in a receptor called the serotonin 1B receptor. And what this shows you is that if we infuse a 1B receptor antagonist directly into the nucleus accumbens, we can block the behavioral effects of MDMA. Finally, and this is a plug for colleagues here from MindMed who are pursuing the possibility that different enantiomers of MDMA may have therapeutic benefit. So why is that? The MDMA that hopefully you guys don't buy off the street but get from a reliable source, and more importantly, the MDMA that people are using in clinical trials, in particular MAPS, is a racemic mixture of two different enantiomers. It's RS-MDMA. And if you go into the literature and you look at the affinities of the R versus the S enantiomer, you look at some of the behavioral assays that have been done, it looks like the R enantiomer has a higher affinity for the serotonin transporter and a lower affinity for the dopamine transporter. And based on our hypotheses, that would suggest that the R enantiomer should still have prosocial effects, but might have a reduced abuse liability. And this just shows in a small number of animals, it's only like 5 it's a very small number, that our MDMA did enhance sociability in this simple assay. So there are actually 2 clinical trials going on based in part on this kind of work. A company called MapLight is pursuing a serotonin 1B receptor agonist in autism, and MindMed is pursuing doing early work to try to get an IND around our MDMA. What does this have to do with empathy? So, as some of you know, MDMA, people in the field, I think, disagree and argue whether MDMA is an empathogen, meaning it actually enhances, in quotes, empathy, however you want to define it, or as you know, who coined the term? Was it Shulgin who called it an entactogen? Is that right, Matthias? Oh, it was David Nichols. I'm sorry, it was David Nichols. In part because does it actually influence empathy? Does it actually influence how I interact with the person in my environment? So we decided to see if we could develop behavioral assays of what I'm going to call behavioral antecedents of empathy in mice. And I'm going to tell you very quickly in the last 5 minutes about some assays, a postdoc in my lab who now has her own lab at UC San Diego, which is called the social transfer of pain. And it's actually a fairly simple assay. You take 2 mice, you put 1 mouse in pain, by injecting a toxic substance in its hind paw. And then you take another mouse, which we call the bystander or observer mouse, and you just let it hang out with the mouse in pain for an hour. And then that observer mouse will exhibit a bunch of different behaviors that indicate that it is experiencing pain. And one way of showing that on the lower left is doing a mechanical sensitivity assay it's a very standard assay in the pain field using things called von Frey, whatever. Again, what you can see on the lower left is the animal with CFA has a very low mechanical threshold for withdrawing its paw, meaning it's in pain. The purple line shows the bystander mouse. So this is a mouse that has never experienced physical pain, just hung out with another mouse in pain. And you can see it manifests behaviors indicating it's actually in pain. And these other graphs just confirm that for about 4 to 12 hours. We also developed an assay of sort of the opposite effect. And this is the social transfer of analgesia. So in this assay, both mice are in pain. So both mice have received an injection of a toxic substance in a hind paw. So they're limping around. We then give one mouse morphine. So it's analgesic. It's no longer experiencing pain. We take our other mouse who's in pain and just let it hang out with the mouse that is experiencing analgesia. And what you can see is that its pain threshold has increased. Its mechanical sensitivity has decreased. That's the blue lines. So it's pretty wild. But again, this should be intuitively obvious if any of you have kids, for example. If you're a parent and your kid is sick, it makes you feel awful. You want to take that pain away. So I am anthropomorphizing this a little bit, but I would argue that these are behavioral antecedents of what we term empathy. So does MDMA affect this? And then I'll wrap up. So this is the key result. This is hot and not published yet. So this is just the pain threshold, the mechanical threshold in the mouse that's in pain. It has a very low mechanical threshold. Here's the bystander mouse. Here now, we only let the bystander mouse hang out with the mouse in pain for 10 minutes, a much shorter interaction period. And in this, for some reason, they show a little bit of increase in their pain, a decrease in their mechanical threshold that lasts about 1 to 4 hours. If we give the bystander mouse MDMA, we dramatically enhance that social transfer of pain. So that mouse experiencing MDMA is now much more sensitive to the affective state of this mouse in pain. And obviously we did control experiments. MDMA itself does not affect pain thresholds. What is this? I'll skip that. What is this? So this just shows you in a different way that direct infusion of MDMA into the nucleus accumbens enhances the social transfer of pain. So in the middle bars graphs on these slides where it says saline, there's a little bit of an effect. There's a little bit of a social transfer of pain, but not much. But in the animals that received MDMA infusion into the accumbens, there's a very clear social transfer of pain. And then, I know I'm going quickly, but the take-home message is we did the same experiment with the social transfer of analgesia, and MDMA IP enhanced the social transfer of analgesia. I don't have time to go through the bar graphs, but you can just see the blue bars are much higher than the other bars. And then finally, we again did the experiment of infusing MDMA directly into the nucleus accumbens. And again, that compared to infusion of saline in the accumbens, that enhanced the social transfer of analgesia. So I actually finished more or less on time, which is very unusual for me. So the take-home message is MDMA promotes prosocial behaviors and, in quotes, empathy. Empathy as operationally defined by these primitive social transfer assays in mice, at least in part by causing large increases in serotonin, specifically in this target region of classic reward circuitry. And this requires an interaction with the serotonin transporter. Serotonin 1B receptors in the accumbens are responsible for some of the effects of MDMA. It turns out the serotonin 1B receptor antagonist does not seem to be blocking the social transfer of pain, meaning there's some other serotonin receptors involved in that. And I would argue, and this is a good topic for the panel discussion, that the importance of this kind of preclinical foundational neuroscience work is maybe by understanding how a drug like MDMA works. Not only can we make better versions of MDMA with more of the therapeutic components of its effects and reduce its potential side effects, its potential toxicity, but I also think by using MDMA as probes, we may actually learn something about the neural mechanisms of empathy and perhaps even compassion. And I would argue what is more important in the world today, given the state of our world. So with that, I will end, and I'm happy to answer any questions. And the people who did the work, I just sit in front of my computer, so I don't do any of this. All right, well, all right. Well, 1, 2, sorry. Go ahead. Because it works. Operationally, it actually, we can quantify pain behaviors using like these mechanical thresholds. It's funny, so you're asking, why didn't we look at the social transfer of reward? Is that, we're actually doing experiments. It's not quite that. I have another postdoc, he's doing experiments. I don't know whether to call it helping behavior, compassion behavior. We're asking whether a mouse will learn to work to give another mouse a reward. So it's not quite answering your question, but and it looks like it's working. And then you can play lots of games with that. One other question.
So I noticed, this might not have been statistically significant, but I noticed that there was one bar graph you showed in the beginning that showed that homozygous certain knockout animals under the influence of MDMA had a reduced social. I wonder if you had any mechanistic insight into why that might be.
That's a great question. I go fast because I don't like people. It's a really, you pay attention to the data. You can work with me. Because a lot of people don't pay attention to the data. So what he's referring to is when we genetically deleted all the serotonin transporters in a homozygous knockout, it looked like MDMA was actually reducing. And the answer is, let's talk offline. I don't have a good answer for that. All right, thank you very much.
Thank you for your talk.